Let's take a look at another example. Again, we want to determine if the set is a basis for P2, the set of all polynomials of degree 2 or less. All right. Now, as we just saw in the previous example, the dimension of P2 is equal to 3. Okay. So the very first thing I'm going to check is, do we have 3 vectors in our set? If we do, maybe this is a basis. If not, then guaranteed it's not a basis. Okay, so let's say I have 1, I have 2, I have 3. I have 3 vectors, 3 polynomials in this set. And so it might be a basis for P2. We still need to check if these vectors are linearly independent. Okay, if they're linearly independent, then because there's 3 of them, guaranteed they will span the entirety of the vector space P2. If they are not linearly independent, then they can't be a basis. A basis must be linearly independent. Okay? Now, we want to know if these vectors are linearly independent. So we want to know if we take the linear combination of these. So let's say a1 times my first vector, negative 3x squared plus 4x minus 3, plus some coefficient a2 times my second vector, negative x squared plus 5x minus 2, plus some coefficient a3 times my last vector, 2x squared plus 4x minus 5. We want to know what solutions we get that make this equal to 0. We know we have one, the trivial solution, right? If I set a1, a2, and a3 all equal to 0, then I get the trivial solution. I want to know if that's the only choice for the coefficients of this linear combination equation that will make it true. Okay, so how do we go about doing that? How do we find all the possible values for coefficients a1, a2, and a3? So what we're going to do is we're actually going to distribute a1, a2, and a3, and then we're going to combine like terms. Okay, so I'm going to get negative 3a1x squared plus 4a1x minus 3a1. If I distribute a2 into my second vector, I get negative a2x squared plus 5a2x minus 2a2. And then distribute a3 into the third vector. I get 2a3x squared plus 4a3x minus 5a3 equals 0. Okay, now let's combine like terms. So my x squared terms, I have this one, I have this one, I have this one. So I get negative 3a1 minus a2 plus 2a3, and then I'll factor out the common x squared. Okay, let's do all of the terms with x now. So that'd be 4a1x, 5a2x, 4a3x. So if I add those like terms together, my coefficients are 4a1 plus 5a2 plus 4a3, and they're all coefficients of x. Okay, and finally the constant terms, negative 3a1, negative 2a2, negative 5a3. Okay, so plus negative 3a1 minus 2a2 minus 5a3. I want this to equal 0. Now, the only way that this is going to equal 0 is if the coefficients of each variable are 0, because they're not like terms, right? The x squared term cannot combine with the x term, which cannot combine with the constant term. So these all have to be 0 on their own if we want the entire thing to be 0, right? So what I could do is I could set the coefficients for each variable equal to 0. So I get negative 3a1 minus a2 plus 2a3 has to be 0. That's the coefficient of the x squared. Has to be 0 if this is going to be 0 at the end. Okay? 4a1 plus 5a2 plus 4a3. This is the coefficient of x. That has to be 0 if I want this equation to be true. Okay, and then the constant term, negative 3a1 minus 2a2 minus 5a3, that has to be 0 if I want this linear combination equation to be true. Okay, notice this gives me a system of linear equations. So I know how to solve a system of linear equations, right? I can grab the coefficient matrix. My variables are a1, a2, a3. I want to make sure this is equal to 0. Okay, we know how to solve this. We're just going to throw this into a matrix and get into reduced row echelon form. All right. If this was anything but 0, of course, we'd augment. But since it's just 0, I don't have to worry about augmenting the matrix. So I'm going to set my coefficient matrix A equal to matrix where the first row is -3, -1, 2. Second row is 4, 5, 4. And the last row is -3, -2, -5. Let's get the reduced row echelon of that matrix. Okay. So this matrix here, the reduced row echelon form of that matrix there, is just the identity matrix. Okay. We know with something like this, we are going to have exactly one solution, right? There are no free variables. I don't have a row of zeros and then a 1 in the augmented part, because remember my augmented part is all zeros. Okay, so A1 has to be 0, A2 has to be 0, A3 has to be 0. That's what these 3 rows are telling me, right? That's the only solution, which means the only solution is when A1 and A2 and A3 are all 0. That's the trivial solution. The trivial solution is the only way to make this equation true. If the trivial solution is the only solution to this homogeneous linear combination equation, it means the vectors are linearly independent. And since they are of the appropriate dimension, they are guaranteed to be a basis for P2. So we conclude, since this is the trivial solution, we conclude that S is a basis for the set of all polynomials of degree 2 or less.